Welcome to this fifth video lesson on work, energy and power. I'm going to start off by doing the solution of the homework that I gave you. And so we're going to look at this example. A ball is dropped from an unknown height. So that's obviously what we need to solve for. We're going to need to solve for h. We've got here that h is unknown. So we're going to solve for h. So there's my data. So h is unknown. We're told that it hits the ground at a speed of 12.52 meters per second. Now, what we mean by this is that, because often learners think, well, when it hits the ground, it stops, so it becomes zero. Now, that is true after maybe a split second. But when we talk about the fact that the ball hits the ground at 12.52 meters per second, that is the maximum velocity that the ball travels before the ground starts to slow it down. So just to make that clear. So we have that velocity, and we now can ignore air friction. We also have the mass as 500 grams. So what we're going to do here now is we are going to use conservation of mechanical energy, and we can do that because of the fact that air friction can be ignored. So we're going to say, okay, so at the top here, this is point A. At the bottom here, this is point B. And we're going to use the conservation of mechanical energy. So we're going to say the mechanical energy at point A is going to equal the mechanical energy at point B. So that means that if we look at the potential energy at A, which is going to be EPA, and we add the kinetic energy at A, which is going to be EK subscript A, this is going to be the same as the potential energy at point B, that's at the bottom, plus the kinetic energy at point B. Now, the potential energy at A is going to be the mass times gravity times the height at A. The kinetic energy at A is going to be zero. Now, why do we know that? Well, because the ball wasn't thrown down, but it was dropped. So if it was dropped, initially it wasn't moving. It was only after it was released that gravity would cause it to move. So the wording is very important. Now let's look at the potential energy at B. Well, B is the lowest point. So that means that here the height is 0 meters, because that's the lowest point, which means the potential energy is 0 joules, because potential energy is mass times gravity times height, but the height is 0. So if we multiply anything by 0, we get 0. The kinetic energy is going to be a half the mass times the velocity at B squared. Right, now with the mass, we need to work in kilograms, so we're going to divide that by 1,000. So the mass is 0.5 kilograms. So we're going to say, okay, so 0.5 kilograms, G, it's on Earth, is 9.8 newtons per kilogram, times the height at A, which is what we're looking for, equals the kinetic energy at the bottom, because all the potential energy at the top got converted into kinetic energy at the bottom. So this is also 0.5 kilograms. I'm going to just put the G there. And VB squared, well, we have VB is 12.52 meters per second. So that's going to be 12.52 meters per second squared. So therefore, we can say, well, okay, we're looking for the height. So this height at A is in actual fact the height that we're looking for there and there. So we can say, well, 0.5 times 9.8 is going to give us 4.9. 0.5 times 9.8 is going to give us 4.9. And then, using our calculators, we get that the kinetic energy equals a half times 0.5, which is a half, times 12.52. And that is going to give us 3.13 joules. So now what we do is we divide by 4.9 on both sides, because at present it's being multiplied, so we're undoing it. We want to take it to that side. So we're going to divide by 4,9 on both sides. So the height is going to be 3,13 divided by 4,9. So we're going to do that, 3,13 divided by 4,9. And we get that the height is equal to 0,64 meters. So looking at this from a conceptual point of view, because of the fact that this object, this ball, is not moving at point A initially, all of its mechanical energy is in the form of potential energy. But under the influence of the gravitational field, that gravitational potential energy gets converted into kinetic energy, and because we can work out the kinetic energy, we can then work out from which height it fell. Now, we use this in hydroelectric power stations where we store water in a dam at a point higher than where the river is below, and this might be a dam wall. Then the water is stored in the dam, but it's actually also storing gravitational potential energy. When we allow the water to fall from that height, like you will see in a waterfall, that by the time the water gets down to the bottom here, it's moving at a very, very high speed. It's got a very big kinetic energy. Now that kinetic energy can be used to drive turbines, which we can use to generate electricity. Let's now consider the final example we are going to do on conservation of mechanical energy. It's what I call the loop-to-loop problem, or the roller coaster problem. In this particular system, we have a roller coaster that has a mass of 500 kilograms, or should I say that a roller coaster trolley, and it initially has a velocity of 2 meters per second as it passes point A, which is a height of 20 meters above the lowest track. And then it's going to move off the edge here, and it's going to be accelerated by gravity. It's going to go up through the loop to an unknown height at B. At B, it's going to be traveling at 1 meter per second. It's going to then come down and speed up, and then it's going to move along this track. And at point C, the velocity is unknown, but then again, this is the lowest point, so we're going to say the height here is 0. Now, we are going to assume that friction can be ignored so that we can use conservation of mechanical energy. When you're in grade 12, we will not ignore the friction, and then we will have to use more advanced formula in order to solve those sorts of problems. So I'm going to ask you to pause the video now and to try and solve for the unknown height at B and the unknown velocity at C. And once you've done it, you can then press play and see the solution. So now we're going to look at the solution. So firstly, I'm going to work with point A, and at point A, I'm going to work out the potential energy. So the potential energy at A is going to be the mass of the trolley times gravity times the height at A. And so the potential energy at A is going to be 500 kilograms. G is going to be 9,8 because we're on Earth. And the height is going to be 20 meters because we have been given that. So if we work out the potential energy at A using our calculator, we're going to work out that EP at A equals 98,000 joules. So that's the potential energy at A. Now we're going to work out the kinetic energy at A. So the kinetic energy at A is going to equal 1/2 times the mass of the trolley times the velocity of the trolley squared at A. So EKA is going to equal 1/2 times 500 kilograms. The velocity at A is 2 meters per second squared. So using our calculators, we work out that 1/2 times 500 is 250, times 2 squared is 4, so that's an easy one. That is 1,000 joules. And now that we have the potential energy and the kinetic energy, we can work out the mechanical energy at A, which is going to be the potential energy at A plus the kinetic energy at A. So the mechanical energy at A is going to equal 98,000 joules plus the 1,000 joules of kinetic energy, which makes the mechanical energy at A 99,000 joules. And that amount is going to remain constant throughout the path that the trolley follows between A to C. Now, because friction can be ignored, the mechanical energy at B is going to be equal to the mechanical energy at A because it's conserved, and we know that this is 99,000 joules. We are told that the trolley is moving at 1 meter per second at point B, so therefore we can work out the kinetic energy at B. The kinetic energy at B is a half times the mass of the trolley times the velocity at B squared. Well, that's going to be easy enough to work out. That is a half times 500 kilograms times 1 meter per second squared. And that gives us that the kinetic energy at B is equal to 250 joules. So now we can work out the potential energy, and the potential energy at B is the mass of the trolley times gravity times the height at B. But now we don't know the height at B, so therefore we can't work out the potential energy at B directly. So this is where we're going to have to use conservation of mechanical energy. So we do know that the mass is 500 kilograms, and we know that G is 9,8 newtons per kilogram, but the height at B is unknown, so we can work out 500 times 9,8 gives us that the potential energy at B will be 4,900 times the height at B, but that's as far as we can go. So what we need to do now is say, well, okay, the mechanical energy at B is equal to the potential energy at B plus the kinetic energy at B. We know that the mechanical energy at B is 99,000 joules. The potential energy at B we know is 4,900 times the height at B. And the kinetic energy at B is 250 joules. So we want to solve for the height at B. So we're going to take the 250 joules across by subtracting 250 from both sides. So we say 99,000 minus the kinetic energy at B, which is 250, is going to give us 4,900 times the height at B. So 99,000 minus 250 gives us 98,750 is equal to 4,900 times the height at B. But now 4,900 is being multiplied to the height of B. So we are going to divide on both sides by 4,900. So the height at B is going to be 98,750 divided by 4,900. So the height at B is going to be 98,750 divided by 4,900, and that gives us a height of 20,15 meters. Now, it's always important to take your answer and to look at its meaning in the context of the problem. Now, when we look here, we go, wait a minute, there's a problem. The height at B is 20,15 meters, but how can that be? The height at A was 20 meters. Surely the height at B should be less. Well, the way I did the drawing, I drew it so as if the height was less. But note here, and this wasn't done on purpose, this was a mistake on my part, that here the velocity is less than the velocity here. Now, if B were lower than A, then some of that potential energy at A would have been converted to kinetic energy at B, and therefore this velocity would have been bigger than at A. So the fact that the velocity is less than at A means that in actual fact that point B needs to be above point A, which is exactly what the mathematics shows us. So this illustrates the importance of taking a look at the meaning of the answers to your solutions. So now let's consider the velocity at C. So if we now look at the mechanical energy at C, it should equal the mechanical energy at B and the mechanical energy at A, because there's no friction, so there are no losses of mechanical energy. There are continual transference of potential to kinetic and then kinetic to potential and vice versa. But the sum of the kinetic and the potential energy, the mechanical energy, stays constant. So we can say that the mechanical energy at C equals the mechanical energy at A, and that's exactly what we're going to do. So if we look at this part of the problem, we can say, well, we know that the mechanical energy at C is going to be 99,000 joules. We've proven that already. The potential energy at C is going to be 0 joules because the height is 0 at point C. We always choose the lowest point to be the 0 potential. So this is where the height will be 0. This will be where the potential energy is 0, which is what we call the 0 potential. So all along here, the potential energy will be 0. So this lands up actually making our lives really easy, because we know that the mechanical energy at C equals the potential energy at C plus the kinetic energy at C. The mechanical energy is 99,000 joules. The potential energy at C is 0 joules, and the kinetic energy at C is a half the mass of the trolley times the velocity at C squared. So 99,000 is going to equal a half times the mass, which is 500 kilograms, times the velocity squared. So 99,000 equals 250 times VC squared. We're now going to divide both sides by 250 to take it to the left downstairs. So we've got 99,000 divided by 250. That gives us that the velocity at C squared is 396. Now, what is the opposite of squaring? Well, that is square rooting. So we're going to square root both sides, and so VC is going to be the square root of 396, which is going to give us 19,8997. That we want to round off to the second decimal place. So VC is going to be 19, and we see that the 9 becomes 10, which makes this 9 10, which makes that 9. So this is going to be 19,90 meters per second. And so when we look at the physical meaning of this, we can see that the velocity is increased greatly from point A because of the fact that all of that potential energy has been converted into kinetic energy. And of course, that's what we experience when we slide down a slope, when we are on a roller coaster, that by the time you get to the bottom, you're traveling so fast that it's uncomfortable. And that's the whole idea, is to scare you. But once you go into the loop, that kinetic energy then gets converted into potential energy by means of increasing your height. And when you come down on this side, there we go again. The potential gets converted into kinetic and gives you a much, much bigger kinetic energy there than what was originally there. So with this example, we now finish off this section on conservation of mechanical energy. And in the next video lesson, we are going to look at the concept of power. And then that will be the end of this section of work, energy, and power for grade 8.